everybody very much interested into AI. AI can almost do everything, right? Especially the previous 5 to 10 years ago is the facial recognition that was actually originated in this faculty, right? Which the Shanghai Sense Time that we invented here actually spread pretty much all over the world, the face scan technology. And then nowadays is about you enter a prompt and then suddenly something generated, right? At the beginning is ChatGPT, you prompt and then generate a text, writing an essay or sending a report to boss. And then later on, you input a prompt, and then it generates a picture, that's story, right? And the one that video I just showed you called Shape-E, or some other many, there are actually many software, okay? OpenAI, the one that I show is far from the best. But just to show, that is from a prompt that you write a sentence, I want something, I want a shark, you input, and then they will generate a 3D shape shark for you. That is Shape-E, and then, oh, I want a shark movie, and then that's Sora, they generate a movie for you. That is all together called a generative AI. Then people immediately ask, why do I do design, right? I mean, my job is gone, right? So no need to do design, right? I just say, I want this thing generated, right? I mean, then obviously in industry, I mean, things going in the opposite direction, okay? In toy making, in animation, that means movie, that may be the direction, but in the industry, things going completely the opposite. That is something I talk about, the so-called I know the name, some people call it generative design. Okay, the name very similar, so I don't use that name. We call it automatic design, okay? This one is able to create a design look like this, okay? And supposedly today, if we have longer time, everybody got a chance to try on your computer. Here, actually, this is where we teach all the generative design. 5 minutes, everybody can learn, actually. But we don't have the time, so we'll just explain what it is and why it is so. Okay, right, this morning, some of you already visit our 3D printing lab, right? 3D printing, I mean, as I explained in the morning, there are total 7 types. 7, right? This is not defined by me. This is 10 years ago, people set the standard, right? The world standard, ISO standard, right? So so I will go through one by one so that you can see the design rules are different. Why we talk about 3D printing. So the one that you have seen, like Adidas shoes, the soft material you see this morning, Adidas shoes, Asus Active Raise, all the protective device is printed using the #1 technique here, called wait for polymerization, right? So what it does is from a liquid reservoir, it pulls something out. I mean, I don't spend too much time explaining it in English, but long story short, video can explain everything.
The Form 1 Plus is a stereolithography 3D printer.
So it's called wait for polymerization. Wait is basically liquid
machine.
reservoir.
Let's start by taking a closer look at the printer. When we open up the light blocking cover, we can see a build platform inside. This metal plate is where the parts are made. Underneath the build platform is a resin tank. This clear window gives the ultraviolet laser a path to cure the resin. To start a print, we'll upload a file and fill up the resin tank to the indicator line. You can see the laser passing back and forth inside, hardening.
Nowadays, I mean, this is less and less. Not using laser pass, but using
We'll
a
take our print
projector,
out and
like
wash
the
it
one
in
that you have
to
seen.
get the excess resin off.
After printing,
The flower
You have
comes with
to clean.
supports on it, and we'll snip them off.
you have to
and finish
remove the
piece.
support. And then that.
Stereolithography is known for producing extreme detail with layers down to 4 times finer than a human hair.
Yeah.
The Form 1 Plus lets us take advantage of a library of materials, so we made some other parts to show what these resins can do. A castable resin gives jewelers and engineers an inexpensive way to produce metal parts. This flexible resin is great for simulating different textures.
Especially good for printing very soft material.
Now let's compare how the Form 1 Plus parts stand up against the filament printer.
Yeah, so you can see this comparing to your home use one.
Feel the ridges.
The home use one, some of have in mind souvenir.
You can see that filament parts quickly snap along the layer lines.
Yeah.
The SLA process creates a chemical bond.
It can be
so our prints take
quite strong and can sustain for a very long time because this one is thermal set. Thermal set, not thermoplastic. So this can sustain temperature for longer time.
If you liked our intro to stereolithography, 3D printing, check
Yeah.
out some of our other videos.
So this one you have already seen. This is mostly thermal set. You have seen it in many of the applications like protective device, like shoes. You have seen it, right? So the next one actually you haven't seen it a lot because this one is for the industry use, so-called binder jetting.
Binder jetting additive manufacturing is a process inspired by the technology of inkjet printers. In this process, a liquid binder is selectively deposited on a powder bed with a printhead. It is a growing process that allows the production of parts for the manufacturing, medical, and dental industries. This technique enables the production of metallic and ceramic parts as well as sand molds for castings. To start the process, a 3D drawing is imported into the printer software. The powder to be used is placed in a dispenser, which ensures a constant supply during printing. First, a powder layer of a specific thickness is spread. Thereafter, the printing head, moving on 2 axes, projects the binder where necessary.
So binder basically
Before moving on to the next layer, the solvent contained in the binder is evaporated by an incandescent lamp. The powder bed is then lowered and a new powder layer is deposited. Therefore, the production takes place in a series of steps that build the part layer by layer. When the cycle is completed, the binder is cured by placing the container in a furnace. The temperature and time depend on the type of binder employed during printing. After this step, unbound particles are removed to reveal the part or the mold. After this step, the sand molds are ready to be used in foundries. The metal and ceramic parts must undergo sintering, infiltration, heat treatment, or hot isostatic pressing before being used.
Okay, this one, binder jetting, is actually good for mass production. One of the, I would say, a very popular application now is the iWatch. The casing, the outside the shell, okay, casing is actually binder jetted. This can mass produce and the price is actually relatively low. Okay, apart from this metal thing that you have seen, like titanium and stuff, actually is very good in terms of making ceramics, like some of the teeth structure, those kind of things. And the third one, number 3, is actually called material jetting. Okay, material jetting is exactly like the home printer. Okay, inkjet machine, right? Home printer. It's just in 3D. Okay, the world maybe the best developed one. Also HP, same HP. Okay, they can print 2D, they can print 3D. Okay, and this one is you see the picture, you know, it's very good in multicolor, very, I would say, vivid demonstration. And it can print very clear polymer.
PolyJet.
You will see it very soon.
Beautiful, precise models.
Beautiful.
Huge
The
variety
keyword is
of
beautiful.
materials and colors.
And much more than you buy from home.
But instead of
Yeah, it's same as the HP
inkjet
printer.
3D printer,
Inkjet printer, same principle.
Plastic. A UV light instantly cures the plastic, solidifying it. And so, layer by layer, complex models take shape. The most advanced PolyJet systems can build multi-material parts. Soft, rigid, clear, and colorful. You can even adjust material properties like heat resistance and durability. The same technology that makes gorgeous prototypes also makes precise manufacturing tools. Designers can predict future needs and serve them now. Manufacturers deliver better products faster and with less waste. Researchers have new methods of saving lives. PolyJet is reshaping industries like film, fashion, and medicine. It's helping people with great ideas improve the future. What's next?
Okay, right. So this one is a bit like inkjet printer. Because it can have many nozzles at a relatively low cost. Actually, it can print very, and it can mixing very well. Because it's come out as liquid jet, small droplet. So it really can mix and making multicolor ones. If you see in my lab, the QR code actually is printed this way, right? The QR code, some of you have already seen, right? So it's very good at, but they only do polymer, you can see, and they only do colorful things, right? I mean, good for demonstration. This is number 3. Number 4 is the most common one, and most people think, this is 3D printing, but actually it's 1 out of 7, okay? It is the one that we see every day, by every home.
It's a game changer. It can create parts and geometries that you can't do in an injection mold.
That's going to create a revolution in the near future, and this technology will be adopted as a major process for manufacturing components.
STEM, yeah. This is what we think that was the 3D printing.
It's a fancy word for laying down a small bead of plastic.
What's really cool is you can have a real engineering grade thermoplastic. So the same stuff you'd injection mold.
Someone needs an ABS or a polycarbonate or a high temperature Ultem.
Yeah, this is for industry use, ABS. What we are printing daily is the cheap PLA or PETG.
Close to the same quality and mechanical properties.
You can see, normally the surface will not be nice.
Part, but you're
You
getting
need additional polishing step,
Our
at least for
software
looking,
is a
for
3D
good
data
look.
file.
Right? If you want the industry use,
Then
that's
that creates a
even
path that's
more
set to
challenging
machine.
thing.
The raw material is produced into filament like fishing line type form. That filament is wrapped around a spool. So that's your
Yeah, this is the one that you
raw
see
material.
mostly,
used
right?
to build parts.
I mean,
That
it used to look like this.
Machine all the way to the
About
head,
10,
where it's
15 years ago,
extruded and
was
refined
first
later.
systematized,
The material is
then made
extruded
into
at the same
system
time.
by this
And then layer by
3D
layer,
system
part is
US
built.
company. But now, of course, most of the company, 9 out of 10 is from China.
Support material is removed. We also offer post-finishing operations that can smooth out those layers. So whether it's a hand,
Yeah, most of the printing will not look good. You
still
need
can
an
provide
extensive
smooth looking
post-processing.
parts.
We developed the technology to fit a full breadth of geometry sets.
But this one, I believe everybody knows it. Everybody seen this machine. Everybody use it.
And new generation.
It's a bit like this. So it is from material they deposit the bits, bit by bit. Okay. So this is only, as you can see, only can use thermoplastic, right? And some of our engineering use, but for our daily use, the cheapest one that we buy, I mean, for the souvenir I give you is PLA or PETG, right? So that's the cheapest one. But for most of the real high-end use one, that means if the one I give you is $1 for the thing that I can sell $1,000 or $10,000 a piece, or even $1 million a piece. I mean, $1 million Hong Kong dollar a piece is actually this number 5, right? Powder bed fusion, and mostly making metals, and mostly obviously not used for our commercial use. It's for defense, for aerospace, and for rockets, right? Like Elon Musk or this Dragon Boat, those kind of rockets. Now, pretty much all the rockets are 3D printed. Okay, not all the rocket components. All 3D printed, and not the old school, no, right? All 3D printed, and the process is like this. So you have seen it in my lab in the morning. So it's from metal powder. We'll quick fast forward, okay? Yeah, it's a bit like this. You use laser or energy beam to scan one layer, and then give additional layer of powder, a new layer of powder you can see, and then you print again. Okay, you may write the same thing or you may write differently, but layer by layer. But because of the powder bed support, actually, they can create very complex geometry. So if you want something very strong, very complex geometry, this is the one. And that's why most of the industry actually prefer this one. Right, so prefer this one. They have many variations, but as you can see in my lab, actually, most of the industry use actually from this. I would say out of 180% actually metal part are made in this technique, not the FDM that you've seen daily. Okay, right? So there may be some other variations, like for this one, E-beam, right? This is to print the aero engine, the fan blade, and also the nozzle. So I mean, there have been many use already in the aerospace, right?
And allows for the creation of
optimized
parts that are not
like
constrained by the limits of traditional manufacturing. RCAM EBM has the unique ability to tightly stack parts within the build in order to increase productivity.
Instead of laser as heat source, this one uses
the
electron
EBM system.
Electron
Following this, metal powder is loaded into the machine. The build chamber is then closed and a vacuum is created to ensure a clean, controlled environment that allows for the processing of reactive material. Next, RCAM EBM's powder layering system evenly distributes a thin layer of powder on the build.
Same principle,
powder bed. 6 kilowatt
but this
electron
is
beam
electron
heats the
beam.
powder bed to the optimum ambient temperature and then proceeds
Electron beam first to heat the substrate,
first contour melting and
then higher the energy and the melt.
Generating the beam contains no moving parts, allowing for extremely fast and accurate beam control.
So you can see the electron beam, it's just all using magnetic force, electromagnetic field, right, to control the electrons and to move to where area that you want.
As each layer is completed, the build is lowered and a fresh layer of build powder is ready.
Yeah, there is a new layer of powder. And one by one, and then
the build is complete,
the whole thing come out.
is extracted, and the RCAM EBM machine is prepared for the next build.
Okay, so this one also the same powder bed fusion, number 5, still number 5, but using different energy source. Most people use laser, right? Some will tend to use electron. Okay, this is for high-end use, right? For those very sensitive materials like intermetallics, titanium aluminide, TiAl, right? So as you can see, this is mostly for iPhone, of course, not using this, right? This is only really only for aerospace and the defense use. And in the world, there's only 2 suppliers. Well, obviously, one from China and one from US, GE, right? So this is. And this one, I think most people haven't seen it. I only see it once in my life, and this is a very funny one. Layer of newspaper, or paper, actually. This is really for fun only, and not really in many use. This one, called sheet lamination.
It feels like a hammer, but how would you like if I told you this is actually made from paper and printed with a 3D printer? This is the M4R, the world's first desktop full-color 3D printer, and it can print a variety of different objects that look almost like everyday life. They are very hefty, very sturdy, even though they are made out of paper.
But this is paper.
So there are actually a couple of different components to this 3D printer.
But of course,
Inside
different
is a
material can be
2D
used.
inkjet printer.
But I haven't seen it in life, actually.
It's printed all the color onto the paper surface. It is then cut out a particular shape that needs to be formed. An adhesive layer is applied, and then a heat plate comes down to press the layer of paper into the one below in order to start forming the shape. The company claims it's 4 times faster than an industrial printer that they have, and you can recycle the waste, plus the printer is using water-based adhesives and inks. This This also means that there are no toxic fumes or powders released. The arc prints at half an inch per hour, which is comparable to other printers like the MakerBot, but it's not the fastest 3D printer on the market. You can get a couple of customizable skins for the printer, including a wood, carbon fiber finish, and a steel brushed finish as well. The M4 Arc will be available for £5,995 or $8,995 US, available in Q2 of this year. For more on 3D printing.
Yeah, so I mean, you can see, I mean, if you sneak peek behind the background, that was almost 10 years ago and not much of the application really. Okay, so this, but still is classified at number 6. Now, because it's processed quite different from others, number 6. So the last one actually quite often used, so-called DD, right, is number 7, right? Number 7 is actually quite often used in repair, in oil and gas, railway service, trains, right? So also you saw it in my lab actually. You saw it in my lab. So it is very dramatic. It looks very busy, right? But actually cannot create a very complex shape. But look very busy. Okay, it looks very complex shape, but actually not. This is mostly used in repair or making something very large, right? Yeah, when they move, it's supposed. This is something like 5-axis. It looks something like this, right? But most likely, a hand is very low. It cannot have that, right? You always come down. That's why. And most easy one is from below. They can put different materials. Okay, right, this is an example of what makes things. If you see, actually, this is they making the rocket nozzle, okay, the nozzle, where you spray the fuel and the rocket nozzle, right? That's for the nozzle bit. And using this technique is very good for making very large things and making repair. So one of the example you will see actually is the sculpture outside the Jianggunnou. Outside there's a sculpture, government headquarters over there, right? That is made by this technique. All right. So with this, I would like to say actually that you can see 3D printing. There are totally 7 techniques. It's not the number 4 only, right? FDM that you have seen. So in industry use, mostly, obviously, it's not designing for toys, right? We are using for real life use, right? And the real life use have many advantages. That means good thing. Why I need 3D printing? Why do I use other thing, right? A few advantages. The first thing people normally use, this has already been summarized. This is already the golden rule. People, there's no argument. We know there are total 6, right? So number 1 is design freedom. You can do some very artistic things. And if you happen to have your so-called shapey, right, or Sora, I mean, Sora is a video, but shapey, you want a 3D object, it look beautiful, you can do that, right? Or you can instant assembly is the number 2, which I give you this morning, is one print, many parts together. No need to assemble them. They can move automatically, right? one example is my little octopus, right? The other one is the shark. I mean, actually, that shark was generated by AI, but just for your example, right? Look good, it can move, and actually, this model sells more than 1 million, right? So more than 1 million, just selling the model only, not selling selling the design only, right? Selling the design only, not the actual printed out parts, right? And very actually for industry use, that's for design only, for art design. For industry, things are different. For industry, most people will tend to use this so-called part consolidation. That means before 20 parts, not only one part. And this is one. This is the if you fly, right, inside the engine, and inside the aircraft engine, they spray fuels, right? This is the nozzle. Yeah. It used to be right, machining, assembly, very costly, and now pretty much, not much, because there are only 3 countries in the world that have the capability to make an engine, right? And you can imagine all of them 3D printed. Okay, if you ask this component, there's no other way of making, all 3D printed. Or the other one to our daily life is drone. Right? There used to be slowly assemble everything, and now one print, finish, continuous print, job done. Okay, no need the assembly. Right? That's another example. Okay, but of course, why now drone? I mean, because this is a high-end drone, but even higher-end drone now they use carbon fiber, right? Lighter, even lighter. So competing with carbon fiber, if you see DJI, they're all carbon fiber one, right? High-end. Right? Even lighter, even stronger, right? So this not the lightest one, right? Because they use a different material. Another quite often used, mass customization. That means 1 million part, 1 million design. Every part, different design, but still can mass produce. One good example is your hand, the other one, very common one, cheese, right? Now even better, the transparent teeth, that one, right? Dental, bracelet, that one. Now all 3D printed, okay? No exception, all 3D printed, right? That's quite costly, right? I mean, Invisalign, that one easily costs you 20K, but the price can drop, right? Due to the maturity of the machine that you see in my lab actually can print that dental one. Right, very transparent. Look as if never wear teeth. Yeah, that one. And you know, everybody teeth different. Everybody has a different design. But do teeth, all these kind of things in Shenzhen, every day is in number of thousands, right? So we need to make in big and the design all different. Okay, 1,000 print, 1,000 design. That means mass customization. Of course, the fifth one is more economical. It's about the shorten the supply chain. Right, that's more for the US story, right? On their side, you can print everything, so less supplier, doesn't depend on East Asia, right? And of course, for our students, we used to do art drilling and do everything, and technician, many, right? But now, when everything we design, we print, right? We design, we print. Very short, right? Very fast, right? Or even can do it at home. Now, we, in promotion of everybody's home should get a 3D printer. Whatever you design immediately come out, right? So this is much faster, right? Shorten the supply chain. But what I talk about today have nothing to do with any of this, right? What I talk about today is something, there's a technical term called topological optimization, also called generative design. Yes. So is, as the name suggests, is an optimization. It's a mathematics, okay? It's a math, right? So what I do is also math. What I do math is, tell me what you want, and based on your condition, I give you the best design. And I promise this is mathematically the best, okay? That if your boss asks you, hey, do we have any better design? Huh? No, this is the best. Unless you ask something different, okay? 100% sure because it's math. So the process of such design, the math, the algorithm, the flow chart is a bit like this, and the design process looks a bit like this. And actually, you see, it's different from AI, right? So AI is just, generative AI is just a summary of existing thing, right? It's a combination of two things, right? Please draw me a cat wearing sunglasses. Okay, they give you a funny picture, but nothing useful, right? It looks beautiful, good, right? But still combination of cat and sunglasses. Nothing new shape, no new shape, right? But this one, no limitation, right? No limitation. So how, but of course, this one have seen it in our daily life already for many years. If you happen to attend morning the lab tour, you see my component, like the heat sink, some of the heat sink, already 10 years ago already using this technique. But of course, now we have 3D printing, we can make things much better. This is one example, right? They even make a bridge out of it, right? The printing process look like this, the design look like this, right? Right, so, right, and the design process look like this, and the end product look like this, okay? Right, so of course I don't have the time, but just put on the Amsterdam Canal, right? So all the design, you just tell me how much is the load from the top, where is your support, how long is your span, and off you go. Give me your best design, right? And the answer is the best design itself, right? So how does that come about, right? So we have to go back to the old school of whatever engineering design, right? We only talk about engineering design. We don't do art design, okay? Do engineering design, normally, we always follow these 4 steps, okay? We take simple example. First thing, we unlike the old, right? The art design. Wow, you have an objective. You think freely. No. Most of engineering design, we do what we want or what the customer wants, whatever asks you to do. Like for example, on top of this building, please give me a windmill, right? And that windmill can power up 1 kilowatt. The first one, 1 kilowatt, right? So that, right, 1 kilowatt is not big, right? But this is, right, well, you can imagine we have space constraint, we have the amount of power we need to generate it, and this is an engineering design problem, okay? We have clear numbers, we have clear constraints, and later on, we have rough ideas. That's called embodiment design. Rough ideas is where we don't touch any software. We just use our hand, sketch, and tell which direction we should go, right? For windmill, we normally have the horizontal one or vertical one, right? So, of course, for this wind in all directions, that kind of thing, right? I mean, in Hong Kong, maybe wind all from north. In the summer, there are wind from south. And from time to time, we have typhoon, from southeast, right? So, wind direction not sure, wind strength not sure. So, in the end, we have to choose one direction to go, right? We ignore completely the other direction, okay? And then we start to open the software, say, the diameter is how much, the power is how much, and we make, and we try, right? That is, this is not what I said, this is what everybody says, right? So this is the engineering design process, right? We ignore about art, we don't think about art. Okay, engineering design, always like this. So translate this one, empty talking, into software, how? Right? You need to, because remember, we need a software to automatically do this. We don't need a human to do this, right? So how, right? This is the software process. In front of the computer, you get all the engineering software, the AutoCAD, the SolidWorks, right? All the engineering design softwares, right? This is the process. But translate that into our software language is, you can see, design specification is where we have all the professional name called objectives. That means what do you want to achieve? Constraints. What constraint that you have? That means I won't only have the objective. It is something like I want the lightest structure, or I want the strongest structure. Constraint is, oh, my space is only one by 1 meter. And the boundary condition is I need to sustain my load, right? I need to sit here and carry 100 kilogram of weight. That's a boundary condition. And given that, we have the initial design. And this is, okay, what we will talk about, right? So how do we do that? Is our current, we only cover the beginning, okay? And later on, we'll go detail, say, oh, the diameter is 4, the height is 1 meter, and something, blah, 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 but come to detail one, right? Later on, translate into something a computer can understand. That's computer-aided design, right? All the softwares, right? So our process, in terms of automatic design, looks something like this. Yeah, it's slightly different. So we give a defined, that means fixed design space. That means you only design within this space, go outside, not possible. And I say, oh, I have my load here, I sit myself here, right, 100 kilogram, and I need to support the ground, right, and I have my space, and what's your objective? My boss say, okay, please reduce the weight by 50%, right, by 50%. And I say, okay, reduce the weight 50%, and okay, I want the strongest structure, okay, strongest structure, 50% of weight, okay, off you go. Right, so why do we do this, and why does it matter with 3D printing? It's because the nature of 3D printing nowadays is by weight. It's similar to you go to the wet market, right? It's by gram, really, by kilogram. 1 gram, $1. 2 gram, $2. 3 gram, $3. What's your design? I don't care. Okay? Design simple, design complex, same price. As long as the weight, same. Right? So that's the nature of 3D printing. And less weight means what? Means cheaper. 50% weight, 50% price. 50% weight, 50% printing time. I can print faster also. Right? If you want something cheaper, faster, and better performance, you need better design. Actually, you can do that. And how to do that? This. Okay? That's why we reduce weight, right? Because a lot are just not useful. So I mask my algorithm. This is my space. I cut my space, right, into small cubes, right? Number of cubes, they call voxels, okay? And I ask each individual one, are you contributing? Right? If the weight there say, oh, I'm not carrying a lot of stress, I'm not carrying weight, or I'm not carrying the strength, okay, I'll just remove that one. It's a very simple concept. Only those useful behind. Remove the not so useful one. Of course, everybody is useful, but some are more useful than others. We have to deal with that, right? We remove all those less useful ones. We keep those small little blocks that are bearing a lot of stress, right? We keep them there and remove 50%, the least useful one. And whatever left behind, I acknowledge, and this is my design. And then in the end, okay, it comes out, right? It's like this. And of course, this is embodiment design, the concept design, right? From the concept, then we go into detail, do a bit of smoothing, parameterization, that means convert it into parameters, and in the end, we come up with a product. And the good thing with 3D printing is I don't care about your design, right? No matter how complex I print, right? As long as you're light, you're cheap, right? So this is the concept, and this is why this thing become more useful, increasingly useful nowadays, right? So you can see it's a clearly optimization problem. We're not talking about statistics, about AI. No, we're doing a pure math question. And right, there is a classic optimization problem that we can, right? We have the so-called objective function. What do you want? What's our criteria for best design? You cannot just say best, right? You need, right? The strongest, what does it mean strongest? Stiffness, Young's modulus, or yield stress, or some detailed number. And the constraints, that means what are the available mean, right? Space is 1 by 1, or space is 2 by 2, or what can you change, right? That's design variable. What can I change? Maybe density, relative density, that kind of thing, right? Or whether I have material density, relative density 1, don't have material relative density 0, or that exactly black and white, right? If I have all the black and white, I have my design, right? Either in 2D or 3D, right? So in the end, right, my design problem is still an optimization problem. I write it as this. This is my objective function. I have certain constraint, and I have whatever that you want to achieve, right? Your function. You want the cost, you want the lift. That means you want the drag, you want the mass. If you want the money, it's also okay, right? This is just multi-objective optimization, right? This is another simple math problem that I think optimization people can do. But write it in short. Yeah, is this right? I want to minimize something subject to some of the constraints, and be it unequal constraint or equal constraint, balance of force, right? Balance of force, right? And allow me to change something that normally is material relative density, right? Relative density 1, I have material. Relative density 0, I don't have material. And we'll just leave it to optimization, leave it to the math to give me the best design. And of course, it takes some time. It goes the iteration. If it's not the best, I go back. But you can see this, everything can be done iteratively by computer, right? You no longer need human intervention, right? So, example, right? We do design, we don't talk empty math. We visualize it, we make it into pictures, okay? So, this is my home balcony, right? I mean, okay, in Hong Kong, relatively rich people can have balcony, right? So, go by balcony, I'm doing there smoking. Of course, most condo doesn't allow that. I do smoking, and suddenly my boss say, hey, expensive, 50% cost cut. Huh? Okay, fine. All right, okay, all right. Let me think, how do I do that? 50% cost cut. If I use 3D printing, that means I need to reduce the weight 50%, right? So, but 50% of weight, to make my structure strongest, so I need to minimize the displacement at the tip. Here, I need to go down as little as possible. So that means the structure is strongest possible, or steepest possible, right? So, okay, weight 50% reduced. Let's go. So how can I do this kind of design? Okay, well, let it to give me design. There are 3 ways actually. Yeah, this is not a joke, but this is true. 3 ways of doing design optimization. And number 1 is size. That means diameter. I only change big, small, but never change shape. Right? The second one, obviously, I change shape. Maybe the total volume I don't change, or the circumferential length I doesn't change. Right? It's like playing with Play-Doh. I stretch, I squeeze, but the overall shape change, but okay, maybe the area change a little bit, but the length doesn't change, that kind of thing. Right? The last one is what we use, so-called topological optimization, or topology optimization. Is at the beginning, I don't know what it looks like. I start to remove not so useful ones. Whatever left behind, I accept it. This is the best solution. Okay? So 3 different approaches. Normally, for simple balcony one, right? You already know a simple balcony can use 3, any of the 3 methods, right? So number 1 is okay, fine, right? I thinking about my finite element idea, or thinking about my calculus idea. This is a whole piece. I cut into 5. I change the diameter of individual one of them, right? So, okay, 5. Number of design variable 5. I just changed 5 diameters. In the end, I got the best shape. It looked like this. Okay, right? But close, right? But if you see, I mean, for this kind of design, you already know the best answer is this kind of triangle shape one, right? I mean that one is very, you can use your mind to imagine that already, right? Close, but not exactly, okay, right? So you see if you have a load coming here, the best design definitely and that look like this, right? It's just how much is the diameter that you want to lay, right? So that one not so. But if about the shape, right? How do I change the shape? Normally people do this, right? I describe the outer curve using some function. People call it the B-spline function. And with this function, I have a number of control points, right? And the moment I move my point, my shape changing together with my control points, right? So if I have 4 control points here, I have x and y, x and y, x and y, so total 8 design variables, right? So with this, I move, and then obviously I change my shape, and in the end, through math, I can get the best answer, right? So this in real life already have many use already, like the hook on the wall, right? Hooking a clothes, you can see you need to add an I-beam here, and if the arm, right, this arm, both sides need to be thick, in the middle is thinner, right? So this already have some real life use already, right? And you can do your multi-functional or multi-objective optimization. But for our one, as you can imagine, our approach looks something like this. Okay, this is my design space. Okay, I cut up into small pieces, and I ask each individual one, are you contributing? If you are contributing, I keep you. If you are not, I remove you. And then 50% I stop, right? And then whatever left behind is my best shape, right? What I ask, the question that I have is 100, 100, 100. I ask individual one, 9 by 3, so total 27. So 27, 9, 27 number of 1 and 0 problem, right? So as long as you can imagine, as long as your pixel is fine enough, like on our screen, right? Our screen is, I don't know, maybe 4K, right? Diameter is 4,000. But normally say, right, is 1024 by 768, that kind of resolution, very low resolution screen, right? So 1 million, right? So we can do 1 million, then everything should be naturally displayed, right? Naturally displayed, right? So look something like this. The design process looks something like this, right? So this is my balcony. This is me standing there thinking how to reduce 50%. And in the end, I end up have a design look like this, right? So 1, 0 problem, right? So okay, I accept that, and then initial and end. But of course, this is not real life use, but more real life procedure looks something like this. Okay, more real life use. So you can see, in the end, it's still, you can see, it's an optimization problem, right? So no matter how we need to, right at the beginning, we have a response curve, and we need to find the minimum solution, right? The minimum, right? The minimum of it, right? We may need to use different optimization algorithm, right? From any random start, right? Then we find the 0, right? The 0 gradient. This is a gradient-based method. But you can see we take tangentials, and when the tangential goes to 0, 0. Very good, right? So, but of course, life will not be that simple, right? Life will not be that simple. If you have this, because at the beginning you don't know where you're starting from. You may start here. Maybe you find the local start here, you find here, you stop, right? Instead of you finding the global optimum. So optimization indeed is not an easy game and very useful for our application. So yeah, so in our university we have many number of professors focusing on optimization. be it gradient based that you can see, and many. And even heuristic based, that means thinking based, AI based. Okay, this bit we use a bit of AI, but still for how do I say, optimization. So optimization. Okay. So to answer the question, apart from Gen AI, how do we do Gen design? We doing optimization. So what are the differences? Is because that only design art. How useful it is, I'm not sure, right? But for our one, I can safely and clearly tell my boss, this is the best design. Okay, this is the best design. Unless you want a different thing. Of course, you want a different thing. The boundary condition change, the objective change, the design can be completely different. Okay, so what is the answer to my question? Now I show. Okay, my balcony. If I say I traditional, right? I cut the top and bottom. Okay, I leave one bar. The deflection, that means how much here go down. This 2.5 mm. Simple 2-bar design, right? Remember, this is what people first. If you're a physics teacher, definitely first thing you can imagine is this one. Immediately, right? Same amount of material, same printing time, same cost, immediately. They're just different design, immediately, 0.8 mm. But of course, if you really bother our topological optimization and use that, in the end, this kind of design, we can further improve it. Right? Same material, same printing time, same cost, even less distortion. Possible. Yeah? So, just to show, okay? Right, but of course things will start to get more and more complex, and you are thinking about the cost. This is using traditional technique. Of course, this one will be more expensive. But remember, for our 3D printing, same volume, same cost. This is the game changer, right? 3D printing, right? The cost will be all the same, as long as you use the same amount of material, right? The printing time will also be the same, right? So that is the game changer. Right, so given the time that I have, right, I only have limited amount of time, so I will not go into the technical details, but just for your information, right? What we are doing here, actually, even in the this technique, topological optimization, almost 100 years ago, but only until the 1990s it became popular for various use. The first user, you can already imagine cars, right? I mean, every year, the car company asks 50% weight reduction, right? Same performance, right? That's the target they do every day, right? Lightweighting, right? So how to achieve that? Is so lightweight, same performance, so you can save your fuel, right? You can make your EV even more important because EV limited battery, right? You cannot drive very far. Only you think become lighter, you can drive further, right? Right, rather than keep improving your battery, right? So it's actually derived this same request, original car company. But obviously, we have many different techniques, right? So including the 100 years ago, the people, American engineer, all right, Michel, or whatever I call him, he said, right, he kept the concept, right, that, how do I design a structure? I don't need to put all the material everywhere. I only put material where they have so-called the principal stress, right? Not only stress, principal stress. That means no shear, right? No shear, right? If you do more so-called analysis, right? So I only put material where they have the principal stress, then I have my design. The concept works quite well, I mean, even until now, right? So if such is so, I only need to design something look like this. A bridge, something look like this, rather than a whole block of concrete, right? And but later on, maybe 50 years, 60 years ago, ground structure method come. Say, I have all the fixed position, and I connect with all the possibilities. I mean, I connect everybody. Okay, everybody connect 1 to 2, 1 to 3, 1 to 4, 1 to 5, 2 to 4, 2 to 5, 2 to 6. Connect everybody. And I remove, then after connecting all, I don't move my ground structure. This is obviously from name you know, it's from civil engineering, right? And I remove those not the bearing stress or not so useful connection. whatever left behind should be the most useful one, right? So in the end, they come like this from here to here. Good design. Okay, the best design. Okay, it works. And at that time, computers start to come in, and people will start to use them, right? So we actually do that, right? Another common used method is called the level set method. This method was invented by our CU, okay, and now widely implemented in every software, okay, engineering software, right? And what it does is, okay, I have my response surface, and I just set the level. It's like water level, up or down, right? If water level down, or maybe like this, water level up, and maybe like this. But good thing, almost immediately, you can use it for printing, right? So, but of course, not every design has this response surface. That's another story. But this is one method that we propose, and and of course there is a so-called voxel one, 3D pixel called voxel, and we ask in each individual one, 1 or 0, but that immediately you can see, right? If it's 100 by 100 by 100, that's already 1 million, right? Your computer almost died, right? 10 million, your computer definitely died, right? You need to buy a new RAM, right? I mean, new memory, right? So you can see it's not that high resolution. Need a lot of computer resources, right? So no. Then later on, another guy from RMIT, then later on moved back to China and invented this method called bezel, like 2 direction. That means I start with somewhere, I can grow, I can shrink, but I cannot generate something out of nowhere, right? It's a bit like the growing and shrinking one. And it also generates some shape, look like this, okay? And the last one, by a Danish professor, right? Denmark, DTU, right? All these guys I mentioned are still alive. They're all alive and still in teaching in their 60s, right? Denmark professor, and this is one of the most common used one called the SIN method. Okay, that means I ask each individual pixel 1 or 0, or why it's called with penalty. Penalty means if it's not 1 or 0, I force you to give you penalty, force you to go either to 1 or go to 0. So you will give me black and white. You know this world, most are different shades of gray, right? And there's no very black and white thing. It's also true in design. But we give penalty so that it converts to 1 and 0, so that give me a very clear answer at least. Okay? 0 and 1 answer, black and white. Right? Black and white. So the algorithm, I know the math is terrible, we will not introduce that, but they need a lot of math. Obviously, this is my penalty curve. You can see with black and white, white is 0, black is 1. 0 means no material, here is true material, and then with this, your performance not going straight line is actually penalized. So depends on your penalty, this can be 0 and 1, step curve, right? 0 and 1, right? But we close to that because to ensure continuity, that means we get a smooth curve rather than very sharp 0 and 1 curve, right? Not good for optimization. So to write that into a piece of algorithm, look something like this. I know it's a bit complex, no need to introduce, and translate the algorithm into picture. Look something like this. Yes, right? So what we do is, you just tell me, the whole design process you just tell me how much load or how much constraint on this side, boundary condition, and what do you want, 50% of weight or something like that. And then you try. Of course, the first try will not, just analyze this. But after my iteration of trying, right, I keep trying, keep upgrading, updating, right? And in the end, we will get the best answer, right? This already, based on this already look a bit like a bridge, right? This is a look in load and support both ends. This is a look like a 100-year-old bridge, that kind of thing. yeah, we are able to design something. We're not talking about the past. You definitely see some of this in your life. This, right? I mean, if you are cycling, it's elastic, right? Or this one is the back panel where the air stewardess or the lady or boy sitting right behind. Actually, the frame look like this. Optimized, lightweighted, reduced weight, right? And this is on A320, right? And all other things. So before I ending this session, okay, you will say, okay, fine, I know, okay, very great. How does it look like in real life? There are many use in real life, but just to show you one video. This video is just from AutoCAD, okay? So a 3 minutes video will explain you almost everything, actually. The process look like this, right?
Generative design lets you design things that weren't possible to design before. So the convergence of cloud computing, new materials, advanced manufacturing, and these new generative design tools are open.
So if I design a drone, the process look more like this. I have my constraint.
You speak in the language of goals
and then off you go.
You frame the problem in terms of what
tell me what's your objective, tell me what's your constraint.
And the computer generates objects.
Yeah, tell me your boundary condition. And yes.
Field as a designer where you're like, I would have
never
gone
this.
that direction. That's
Okay,
really interesting.
right. Depends on your trade-off.
But this is opening up my space of possibilities. The HackRod project, so we just took an off-the-shelf race chassis and put 56 sensors on the tension points of the chassis. The HackRod team drove that thing out in the desert under extreme conditions.
From there, that data was analyzed and input into one of our generative design systems, DreamPitcher, and a new chassis was grown.
So this is one of the first times.
This is just AutoCAD, okay? This is just AutoCAD. Actually, just to show that actually every software, every engineering software has this. So it's just people haven't realized this partnership in the software.
As these things become easier, there are going to be more entrants in every market.
Yeah, this is an example of the partition wall of A320.
Car manufacturers, it means that they've really got to be looking at how they can start to adopt this stuff today.
The human brain can hold 5 or 6 variables at a time. The computer doesn't have that limit. So with generative design, what you're trying to do is put all these conflicting...
Yeah, this is the one I mentioned, the ground structure method, right? And then they do a Pareto front, right?
What I really
Optimization, classic. Then
elbow
you do
chair
the trade-off.
is that we're considering
people can choose
manufacturing and
right?
CNC. So rather than
this is another example. At the time, no 3D printing, right? Still a CNC cut out. But just to classic question. I want to see these people, how heavy, and where's the support, and give me your light structure, and then off you go. Yeah, this is what I input.
Letting the computer decide and give you hundreds of different options.
And then off you go.
Preference, including materials.
You give me your design. And then the software will start to generate, many actually. Yeah, so this is the new automatic design procedure that I'm talking about.
Appreciate this.
That was 2 years ago.
15 years in the NBA. That was a bad boy. Yes, he was. Oh my God. Separated my shoulder one time. Is that filled with diamonds or something?
You can see the lightweight design comparing to
So is it heavier than a regular basketball? I think he gave it to the judges to show that it was the same size, same weight.
This is father and son.
He says this don't
K.M. Martin Senior and K.M. Martin Junior. This is father and son. So his father passed the ball to his son, and then his son supposedly slammed down inside the basket. Okay, no. Oh, fast forward. He fell 2 times. Okay.
There you go. That's it. Jimmy, I don't know. I pay homage to my dad, and I don't know. Right? Okay,
yeah. So this is the story behind the making of it, right?
When I started at Wilson, my boss, Kevin Krishak, charged me with the task of reinventing the basketball.
A project like this begins, again, because we go back to, we're always trying to look at what's, new cutting edge technologies.
The technology that really struck me was additive manufacturing, because it just enables so much change about the ball that can completely alter the athlete's experience, the way it's made, everything that we care about. The engineers started working together with industrial design. So bringing those two together, we were able to come up with several designs that we then later iterated on that resembled a basketball, felt like a basketball, but also performed like a basketball.
And the most important part of the formula is the player, right? Because if the player doesn't love it, then it's not going to be a product or a prototype.
We met with General Lattice. We made our design with them, and it was translated to a digital file that can be read very easily by the printer. We sent that file to EOS.
Working with a brand like Wilson is a little bit different for EOS because we are traditionally working with aerospace companies, automotive companies.
Yeah, it's mostly for automotive aerospace.
Manufacturing was the right choice for the airless prototype because first off, it's literally the only technology on Earth that could bring this concept to life.
Yeah, it's
so
because
what happens is there's
very
a powder
compact
bed
shape, as I
that's
mentioned.
Swept across, and then a laser almost etches sketches a pattern in 2 dimensions. And as this process iterates over and over, you end up with a 3-dimensional ball.
Yeah,
moving
this
that
one
powder
you
from
see
the ball without damaging the ball.
It's not
kind
of
of
good
like
quality, right? It's
an archaeological dig.
In my lab, right?
And at
in
that
the real
point,
use,
the
it's
powder
something
is
like this.
sealed using a smoothing technique, and then dye is penetrated and reacted with the
you need to
polymeric
surface
surface.
polish a little bit.
After that process was complete, we would send the ball to our NBA test facility in Ada, Ohio,
you print it, you
where
dye
they
it,
would put the ball
done.
through rigorous testing.
It's the same to the.
This is only a dot on the development path, but we're really excited about the first step that we have here.
I mean, that's our goal. That's our job is to push boundaries, change perceptions of the brand.
But this is what we call the one. Basically, this is like, let's make one and let people enjoy it.
So this one, no need pumping air anymore. And very self-clean, right? If you feel it's not clean, you just wash it with water, job done,
It's
you
just
play it again.
such an incredible process, such a life-changing process for me.
Okay, right. So yeah, that's all of it, and hopefully we can design with 3D printing with more of this kind of things in the future. Yeah, that's the true end. Yeah. Sure. So because today time limit, I haven't had time to explain the algorithms behind.
Artificial intelligence is changing.
Yeah, so I haven't got time to explain how the AI works, how the AI generate this model, right? It is actually that's a really long story because this one doesn't have a short answer. My one optimization actually relatively easy. AI, because it's a black box, is hard. I only can explain how they do the statistics. So that's why I mentioned if you use so-called generative AI to generate, use the prompt, and then it will generate. It will give you a best guess, but based on past experience, based on what he learned. You see what I mean? So what he learned or what he generated, he will not. In that sense, he will not generate a new thing. You want a shark, you train him 1,000 sharks, it will generate a shark. It will not give you a new look shark. No. Yeah. So it's a combination of all things, and maybe animation, maybe a toys like the shark I give you. That one is very good at. But if you want, I want a completely good design, new design. I want something that is definitely optimized and is the best. You know it's the best for a certain purpose. I see even in recent or midterm future, AI will not be able to do that. So clearly, we can see. I mean, of course, this is not cast into stone, final answer, but we gradually see the trend separating. For AI, the generated one, they are really eating into toy making animation, video, going into really going into that direction. But for this so-called generated design or automated design, they were really going into engineering design. Not really innovation, but engineering design or best performance. Give me your best performance, that kind of thing. Or subject to certain condition, that kind of thing. So they are seemingly going into different direction. So it depends on what you need.
Thank you for answering. Follow up. So why can generative AI be used in engineering design?
You try yourself, then you know.
So
you give the same thing, you try. You give the same thing, you go back, and because there are many software, you try the same thing. Oh, I want the stiffest structure with the weight of 50%. And with the boundary condition of in X and Y, there should be fixed, Z, there should be free rotation. You go back and try. See what kind of answer it give you. You can see. If there's no past experience, he cannot answer you. But he will try pretend he know everything. He will give you an answer. Don't worry, that's what generated means. No matter how, correct, right or wrong, I give you an answer. You believe me or not, that's not my problem.
I get your point, and also have some experience with AI. So nowadays in engineering design, all the functions and all the performance optimization part is still there are engineers who will roll those functions.
Yeah. We increasingly using AI now. No joke. Increasingly use. Where to use is inside the software. Some sub-function to use, like say mating. These two match together. Before it match, please match. Overdrive, right? Now this two phase, please match. If there's small error, they will just automatically smooth out. There's already, I haven't shown you the video, but there's already here and there many places using AI. In AutoCAD, in SolidWorks, already a lot of use. It's just not in the whole, embodiment design, not yet. Yeah, thank you. So well, maybe next year you come back and try the software. Try. Yeah.